All right, this is the 2.1 lesson video for AP Calculus BC. And what we are going to discuss in this video is really the beginning of our derivative unit. So we've been spending the first few days spending a lot of time on how to solve limits, how to interpret limits, and now we're going to make the transition into going from just limits into really the definition of a derivative. As we go through this today, we're going to be talking about tangent slopes a lot, and we're going to talk a little bit about instantaneous rate of change. And what I want you to realize as we go through this is really what we're doing is we're discussing the idea of the derivative at a point. So we're not finding a derivative function today, we're finding what the value of the derivative at a point is. And when I say the derivative at a point, that is the instantaneous rate of change. That is also known as the tangent slope. So all of those are sort of interchangeable terms. So when you see the terminology that's used in your book, in these notes, and other places, what you need to realize is that they're all basically meaning the same thing. It's just a different way of presenting it. And what they're trying to do in this section is transition you slowly into the idea of a derivative. So what we're looking at here is the idea of how to find a tangent line and how to find a tangent slope. So we looked at this a little bit previously where we had 2 points and we were trying to move the 2 points closer and closer together to approximate a tangent slope. And we were doing that with a bunch of secant lines that were, being formed by those 2 points moving closer and closer together. So this is that same idea. And the first part is when I want the equation of a tangent line, it's just the equation of a line. The only difference here is I need to have a point of tangency, and then I need to have my tangent slope. So when you see what's in this box here, this part of it, that's what you know from Algebra 1. Y minus y1 is equal to the slope times x minus x1. It's just written in a different form, but it's as simple as the equation of a line. Okay, so the second part of this is where we're starting to get into the idea of a derivative. So when we find the tangent slope, notice what we're using here. So let's look at this diagram down below and take a look at how this is referencing the slope. So it says f of x minus f of x naught. So notice what we have here is we're looking at these points P and Q like we have looked at previously. So the point P here, notice that it's at x naught, f of x naught. The point Q is just sort of a general point. It's at some point on my function. So we're going to say it's at x, f of x. So all I'm doing is y2 minus y1 over x2 minus x1. And if you look down or back above here, the limit as x approaches x naught, that part of it is new, but the part that you should recognize from Algebra 1 is this piece. That's my y2 minus y1 over x2 minus x1. So it's not anything more complicated than that. And what's making this now go from being just a slope into a tangent slope is the fact that I'm applying this limit. The limit as x approaches x naught. That's making essentially the point Q get closer and closer to the point P, and that distance is going to get infinitely small, and that's going to allow me to find that tangent slope. Okay, so let's take a look at an example here. All we're going to do is use that definition that they gave us for the tangent slope to find the equation of the tangent line for the graph of x squared at x is equal to 5. Okay, so from what we had above, the slope of our tangent line in this case is going to be equal to, well, our definition said the limit as x approaches x naught. So I'm going to do the limit as x approaches 5 because our x naught in this case is 5. And then I've got my f of x, which was x squared, my f of x, which is essentially f of 5, or f of x naught, I should say, was f of 5, and that would be 25 because 5 squared is 25. And that's divided by x minus x naught, or x minus 5. Now, we solved a bunch of limits like this previously, and at this point, this should be something that you can kind of look at and know how to solve. But what you could do here if you need to solve it is you can factor the numerator. The x minus 5s will cancel, and you'll be left with the limit as x approaches 5 of x plus 5, and that's going to give you 10. So 10 is my tangent slope. Now remember, whenever we write the equation of a tangent line, there's two pieces of information that we need to have. We need to know the slope and we need to know the point. Well, my slope in this case, my tangent slope was equal to 10. And the point that I'm dealing with here is the point 5, that's my x, and then the y coordinate was 25. So with those two pieces of information, I can write my equation as y minus 25 is equal to my slope times x minus 5. Okay, now when you write the equations of your lines, I really would prefer that you leave them in this form because that's the form that we're going to write equations in when it comes to linear equations. And then further along down the road, when we get into Taylor series in the second semester, we want to be able to reference that point of tangency, which eventually we'll start calling it the center point. But that point of tangency can still be referenced when I have it in this point slope form. If I put it into slope intercept form, then I'm going to lose this reference that I have right here to the point 525. So keep that in mind. Kind of get in the habit of leaving them in that form. And then when needed, you can just isolate the y, just add the 25 over when you need to. All right, let's move on here. There is another way that we can write the tangent slope, and it's just a different notation. It's the same idea with a slightly different notation for how we're going to reference these points. So what we're talking about is still the point x naught being our point of tangency, but then we're just going to say instead of having some general x, we're going to use h units away from that. So notice here on this graph, I've got this point P again, it's at x naught, f of x naught. But now for the point Q, we're referencing it with x naught plus h, and then it would be f of x naught plus h for the y coordinate. Everything else about this is exactly the same as we just did. We're doing the change in y over the change in x. So that's this part, my slope, change in y over change in x. And then I'm taking the limit as h approaches 0. Notice the change of x in the denominator just simplifies down to h because we had x naught plus h minus x naught. So everything cancels out but the h. Okay, so just a different way of doing the same thing that we just did. All right, so what I'd like for you to do is try to solve this problem down at the bottom. It's the exact same thing that we just did, just using this now new form for finding the tangent slope or the definition of a derivative at a point. So they're asking you to find the equation of the tangent line for x squared at x is equal to 5. We already know what the result is because it's the exact same problem. The only difference is I want you to use this alternate definition that we have now for finding the tangent slope. So pause the video, and then when you unpause it, I'll show you what you should have for your solution there. Okay, so here's what you should end up with on that one. It says find an equation of the tangent line to the graph of f of x equals x squared at x is 5, just like before. And notice my setup. My limit as h approaches 0 of f of 5 plus h minus f of 5 divided by h. So I just wanted to make it really clear how I plugged into that setup that we had up above. And what's more difficult about this setup is that we actually have to go through and do a little bit of algebra on this one. 5 plus h, I'm plugging into x squared. So I'm going to expand that out. And that's where you see this 25 plus h squared, or 25 plus 10h plus h squared that you see right here. That was 5 plus h being squared. F of 5 is still 25. And then you just go through and simplify out. Whenever you solve the limits in this form, and you're dealing with the definition of a derivative or the tangent slope or the instantaneous rate of change, whatever you want to call it, in this form, this h should always cancel out when you're dealing with these polynomial functions. So if your h doesn't cancel, the h in the denominator, if that doesn't cancel, then you know you've done something wrong. In this case, the h canceled. I'm left with 10 plus h. Take the limit as h approaches 0. I got a tangent slope of 10, which we already knew was going to be the case. And then down below, you can see the equation of your line again. So again, very simple. Not really anything difficult to do. The only thing that might be a little bit challenging in this lesson is that sometimes the algebra can get, just a little bit tricky when we don't deal with polynomial functions. When we're dealing with rational functions or we're dealing with square root functions, we're going to have slightly different steps. But really, the overall concept is what I want you focused on, and the overall concept is the exact same from problem to problem. So you shouldn't have too much difficulty with it. Okay, so now that you've had a chance to work those out, you can see the result of the first one. I chose to use the form here where the limit as x approaches x naught of f of x minus f of x naught over x minus x naught is going to be equal to my tangent slope. So you can see on this one, there's a little bit different algebra involved, and really we end up dealing with complex fractions here. And so you've got to do a little bit of work to simplify your complex fraction, and then that's going to allow things to cancel out. So I'm not going to go through all the algebraic steps here because that's part of what you should have looked at when we were going through that prerequisites unit, but I just want to point out a couple of things here. So right here on this step, you can see that's where I identify that I'm sort of stuck with a complex fraction. And remember, the way to deal with this is to get a common denominator in the numerator, multiply by 1 over x plus 2, and then from there, you can see that I can factor and make the x plus 2 cancel out, and that gives me my tangent slope. Now, notice I've got the equation of my tangent line, and then for the normal line, the normal is just the perpendicular line to the tangent line. And the reason that we're going to talk a little bit about normal lines is because a lot of what we do in calculus eventually is going to be tied to vectors, and we start talking about normal forces and normal vectors and things like that. And so you'll see that terminology used from time to time in some of these beginning calculus examples that we do. And it's because eventually, if you get into vector calculus, you're going to start to see a lot about normal lines, normal vectors. So that's something that I'm just trying to get you ready for. Okay, so for the second one, you can see that on this one, I chose to use the second form that we had, which was f of x naught plus h minus f of x naught divided by h. And for this, it's going to give you a limit that looks similar to one of the limits that we discussed a few days back, where we've got a square root in the numerator. And if I try to do direct substitution, I've got 0 divided by 0. So we're essentially going to multiply by 1, which is what I've done right here. So I'm multiplying by the conjugate, which is essentially multiplying by 1. So I'm not really changing anything about this expression other than what form that it's in. And by doing that, what I'm hoping is going to happen is that something's going to cancel out, ideally the h in the denominator. The h should cancel out, and that's going to allow me then to actually solve this limit. And you can see I get 1 over 2 root 5, and then it's just a matter of getting the equation of the line. So the only thing missing for the equation of the line in this case was the y value, because we knew x was 1. So f of 1 would be 5, and so, or f should say f of 1 would be square root of 5, and from there then I've got the equation of the line. Okay, so fairly simple to do. And really, for the most part, what's in this section, it's not difficult. It's just that it's the foundation for what we're going to do moving forward. Okay, so the last part of this is just taking that exact same concept and applying it to motion. So in this class, what we're going to use as our primary application for our basic calculus ideas or concepts is going to be motion. So position, velocity, and acceleration. So those are closely related in both the forms by taking derivatives and also by taking what we call antiderivatives. So for now, we're primarily just going to be focused on position and velocity. And if I get the rate of change of the position, that's going to give me an average velocity or an instantaneous velocity, depending on how I choose to measure that. So notice that for this first calculation here, we're talking about having position at 2 different points in time. We typically use S for position, V for velocity, and A for acceleration. So if I want to find my average velocity, all I'm going to do is figure out how far did I move, how long did it take. I'm going to divide those 2 things out, and that's going to give me my average velocity. So you can see here in terms of the notation that I'm going to use, this is the notation that I'm going to use. My position at my finishing time minus my position at my initial time divided by the change in time. So that's my average velocity or my average rate of change. So that's like getting the slope between 2 points, right? If we want to think about this in more of a general sense, that's what we were doing at the beginning, getting the slope between 2 points. Now, if I want to get an instantaneous velocity, what I want to do is I want to make that time interval get very, very small. I want it to get infinitely small. So to do that, we take the limit as that h time difference approaches 0. And so now this is essentially exactly what we were looking at before when we just had this in a general form. Now we're looking at this in terms of velocity and position. If I want the instantaneous velocity, it's the second position minus the initial position divided by the change in time. Then we're taking the limit as h approaches 0. So you can see graphically down here, we're still dealing with the exact same setup. So everything's the same. The only difference here is instead of referencing just a general function value, we're going to reference that function to be position. So pretty straightforward. All right, so you've got one problem here I want you to try. So just read through this. The main idea is you're finding an average rate of change and an instantaneous rate of change based on this position function that you have. So you can pause the video and then try to work it out. And then when you unpause it, I will show you the solution. Okay, so here's what you should have come up with. For my average velocity, it's just the finishing position minus the starting position over the change in time. And so I've got, in this case, my position at time 4 would be 5. My position at time 1 is 4. And my change in time is 3. So my average velocity here would be 1/3. We don't have any units here, so I'm not going to worry about units. If it did have units, we could put units in there. And then when I want the instantaneous velocity, that's where I've got to now take the limit as the distance between those 2 points approaches 0. So notice that it says the instantaneous rate of change at time is equal to 5. So I know I'm starting at 5, and my second point is going to be some tiny distance in the future. And we're just going to say that's h units of time away. And we want to take the limit as that h approaches 0. This is actually the exact same setup as one of the problems that we saw earlier. We got 1/2√5. Okay, so again, not really difficult stuff, just one of those things you need to practice a little bit. When you go through Wiley Plus, you should get enough practice with everything that you're going to see. The main thing is make sure you know how to solve these limits out in both forms and also be able to identify what those forms are. And then finally, there's 3 types that you really need to know how to do. You need to be able to do these limits with a polynomial function. You need to be able to do them with a rational function, and you need to be able to do them with the square root function. Okay, just email me or you can message me if you have any questions, and we'll see you soon.